This next section of chapter 17 is going to talk about pressure. So the first thing to recognize is that enthalpy is not pressure dependent. So pressure is not related to the heat of the reaction, but because entropy is related to volume. So remember, the bigger the volume, the more entropy you have. Volume is indirectly related to pressure. So you can actually talk about how pressure affects entropy. So if you have a large volume, like I said, that's going to be more entropy than a small volume. So that means if you have low pressure, that's going to be more entropy than if you have high pressure. And this leads us to our next equation where you can calculate pressures or use pressures to calculate delta G. And it's kind of a specific equation. So the first thing to recognize is that there's two delta G's. One of them has that little zero symbol. And remember, that means at standard states. So you can find that delta G by doing the products minus the reactants. So first, you would take the sum of the products, don't forget to multiply them by their coefficients, and then subtract out the sum of the reactants, the values given, and plug all that in for the delta G naught, which is that little circle. Then you can add it to RT natural log of Q. So let me just go through each one of those. R stands for the gas constant, which sometimes is things like 0.0821. It can be 62.4 depending on the units, but in this case we're going to use the other R value, which is 8.3145, because this one has units of joules per Kelvin per mole. So we want to talk about energy, so that's why we need it to be in joules. So do make sure that you use the correct R value there. Temperature is going to be in Kelvin. Ln stands for natural log, which is a button on your calculator. Most of you probably know what that is. And then Q goes back to equilibrium. So remember, Q and K you calculate the same way, products over reactants, raised to the power of their coefficient, don't include solids or liquids. And that can be in units of concentration or in pressures. So if they give you pressures of things, you can plug it into Q just like you would for K. So again, products over reactants raised to their coefficients. And then you can plug that all in and get delta G. Now, here's the cool thing is that now that we're talking about equilibrium, the first thing to recognize is that equilibrium point occurs at the lowest value of free energy available, which means delta G equals 0. That's the lowest energy you can get. And also Q is equal to K at equilibrium. So if we take this equation from up here, we had delta G equals delta G naught plus RT natural log of Q. And we're going to plug in 0 right here. So now we have 0 equals delta G naught plus RT natural log of Q. And then we can rearrange it so that we don't have 0 on one side. So if we subtract RT natural log of Q by both sides, that's where they're getting this. Also, notice that they switched Q with K because at equilibrium, you talk about K and not Q. So that equation can be used if it says it's at equilibrium, which it will tell you in the question. All right, this next section, again, is just relating the delta G and the K. So notice that delta G equals 0 when K is equal to 1. All of that is happening at equilibrium. If delta G is less than 0, meaning it's negative, then that means K is greater than 1. It's proceeding to the right, and that's called exergonic. If delta G is greater than 0, K is less than 1, that's going to be endergonic. And now we have a whole bunch of equations that we can use. So again, it just depends on what information they give you as to which of those equations that you would use. And then the very last thing for this chapter is just talking about how all this relates to work, and work means the energy to actually do something. So the maximum possible useful work obtained from a process at constant temperature and pressure is equal to the change in free energy. That's just a fancy way to say that the free energy is energy that is free to do work. So the maximum amount of work is equal to the delta G. However, the second one says the amount of work obtained is always less than the maximum. And I liked this next section. You don't get a lot of humor in chemistry textbooks, so I thought this was funny. It says the first law says that you can't win, you can only break even, and the second law says you actually can't even break even. So what that's all saying is that the amount of available free energy of our system is actually decreasing. And what the important word there is the free energy that they're talking about. And that is it for chapter 17. Good luck on the progress chapter.